Welcome to part 11 of Preparing for Organic Chemistry, Intro to Reaction Mechanism. Okay, well, what is a reaction mechanism? Let's take a simple example, the gas phase reaction between nitrogen dioxide and carbon monoxide to yield nitrogen monoxide and carbon dioxide, okay? Double replacement type reaction. Is this the mechanism of the reaction? Probably not. This is the overall transformation. Okay, it doesn't tell you how the bonds are broken and bonds are made. It doesn't tell you how the transformation occurs. Okay, this is the overall transformation, not the mechanism. Mechanisms are comprised of one or more what are called elementary steps. And an elementary step is what it sounds like. It's a chemical transformation that can't be further broken down. Now, before when I showed you this example, I said this is an overall transformation and not a mechanism. And that's because I happen to know that. There's no way for you necessarily to know that. There are certainly examples of chemical transformations in organic chemistry that are one-step mechanisms, in which case the overall transformation is the mechanism. Okay, but that's not the case here, and I probably should have said so. All right, so if that's not the case, and this is an overall transformation, then the mechanism might look like any of these three possibilities, right? In the first of these three, there's a two-step mechanism. In the second of these, there's another two-step, and in the bottom, there's a three-step mechanism, right? So it could be any of these three. Is that right? No, that's not right. It can't be the third one. Why not? Why not? How do I know immediately that whatever the mechanism of this reaction or transformation is, it can't be the steps that I've indicated in the third entry? It can't be. Why is that? Well, for the simple reason that if you add those steps up, they don't add up to the overall transformation. You have nitrogen as a product, and you have oxygen as a product. If you add those three steps up, you have N2 and O2 as products. And since they don't appear in the overall transformation, that can't be the mechanism. So the first rule that you've just learned for writing a reasonable reaction mechanism, and that's going to be the language that you're going to see from your professor, the first rule that you just learned is whatever the mechanism that you propose is, it better add up to exactly the chemical transformation, including the stoichiometry. Otherwise, it can't be the mechanism of that reaction. So which one is it? Is it the first one or is it the second one? It turns out it's the second one. The second set of steps is the reaction mechanism, is believed to be the reaction mechanism for this chemical transformation. And I say believed to be because we can never know for sure. We can never know for sure because the reaction mechanism is determined by experiment. And so you can see below that someone did a kinetic experiment and determined that the rate of formation of nitrogen monoxide, that's what you see there, DNO/DT, the rate of formation of the product nitrogen monoxide is proportional to the square of the concentration, time-dependent concentration of nitrogen dioxide. Okay? So that's the rate law that's experimentally determined, and that rate law is consistent with the bottom reaction mechanism, right? Which involves two molecules of NO2 versus the top reaction mechanism, which only involves one. Okay. So reaction mechanisms are experimentally determined, and since someone could perform an experiment tomorrow and gather data that would be inconsistent with the reaction mechanism that, say, you proposed today, that's why we say you can never know the true reaction mechanism. You can rule out reaction mechanisms, but you'll never know the true one. All right, so before we get into this, why do we care? Why do we care? Seems like a lot of trouble to go to determine the reaction mechanism for a chemical transformation. Who cares if we know the net result? Turns out knowledge of the reaction mechanism is vital for two main reasons, and here they are. Number one, it's the best way to learn organic chemistry. Okay, there's a limited number of reaction mechanisms, and they have a lot in common. And would you rather learn, say, 20 reaction mechanisms than memorize 10,000 reactions? That's what it comes down to. Okay, reaction mechanism is how your textbook is organized. It's how your professor has organized his or her course. So it's how we learn the subject. That's pretty darn relevant. The other reason is, if you want to improve a reaction, why do we run chemical reactions? For two reasons, maybe three reasons. Okay, number one, perhaps to provide energy, right? Combustion chemistry. Number two, to make a valuable product. And number three, possibly for, forensic or analysis reasons. But let's look at number two, to make a valuable product. Well, you want to make as much of that product as possible, as efficiently as possible. You want to optimize that reaction. Suppose you're working on your car's engine. Okay, would you open the hood to your car's engine and begin tinkering around if you didn't understand exactly how your engine worked? No, you wouldn't, but you do want to optimize the efficiency of your engine and the power of your engine, and so you need to know what's under the hood and how it works. That's why reaction mechanism, these two reasons, those are two good reasons. All right, so how does this pop up, say, on assessments? This is a very typical problem. Right, you're told that 1,3-butadiene reacts with one equivalent of HBr. Right, you're given reaction conditions to give 3 isomeric products, each with a formula C4H7Br. Part A, what are the structures for these 3 products? Part B, how are they formed? Propose a reasonable mechanism. Well, you can't really answer A without knowing B. All right, propose a reasonable mechanism. What does that mean? What does that mean? All right, in the next lecture in the series, we go into exactly what that means.